let us continue, and a little bit iffy. The first topic that we need to discuss to be able to discuss the GLM at all for fMRI are matrices and calculating with matrices. So for everyone who has had a course on linear algebra, that's basically just repetition for you guys. For everyone else who hasn't attended a course on linear algebra, first do that, and second, it will be some novel stuff, but very important stuff. Also on these slides, essentially for the first 4 sessions or so, I put up what I regard as useful prior knowledge, because we can't start here with everything. So I need to, as I said, I started somewhere kind of in the dark, thinking, okay, here we can start with matrices. Of course, it doesn't hurt if you are familiar with sets first, and how to write sets, know about functions, vectors, and also know a little bit about programming, as I will show little bits and pieces of Python code in between. If you are new to all of this, or if you haven't heard these things since school, there's this Mathematischer Vorkurs Fit für Psychologie happening every autumn, and this is also a link here, so you can go to that and familiarize yourself with these topics. It's not essential for today, but it's helpful. And I also need to apologize in advance for the typos that will come up on these slides. I designed these slides de novo in the last week or so, and when I present them for the first time, then that's when I see the typos, so sorry for that. I hope it will not be too confusing. So why talk about matrices at all? Because they are the words in the language of the GLM. So you cannot really talk about the general linear model as the model that encompasses all of your undergraduate statistics, so a model that unifies simple, multiple linear regression and t-tests and ANOVA and ANCOVA. And if you go a little bit further, also MANOVA. You cannot discuss this model if you, and also understand this model if you cannot even really understand any SPM analysis if you don't know what matrices are, because you will always be looking at design matrices. So it makes sense to be familiar with matrices, only for the purpose of GLM for fMRI, but also in general for any kind of data analysis that you're doing. So in fMRI GLM, the model formulation is based on matrices. The experimental designs are special matrices, namely the design matrices. The data are special matrices. They are vectors, so one column of a matrix. The model parameters are special matrices, so they are vectors again. And then also the probabilistic assumption that feature in the GLM are encoded in covariance matrix parameters. So everywhere matrices are featured, and you need to understand a basic set of things that you can do with matrices. So it's good to familiarize yourself with those things, and if you heard them before, also to from time to time refresh your memory. So it's really essential. There's no way studying the GLM without matrices. Doesn't work. So what we are going to do is first give a definition of what matrices are, and that's fairly straightforward, and then discuss a set of operations on matrices, most of them which are also quite straightforward, except maybe for 2, namely matrix multiplication and matrix inversion. So there we spent a little bit more time. So that's on operations. Then determinants. Briefly, we don't really need them, but we will see at least one determinant all the time in the Gaussian, so that's why it doesn't hurt to be briefly reminded about determinants. And then in the end, just some special matrices, essentially just a little bit of notation, roughly to know what I'm talking about later on. There was something on my mind. No, I forgot it. It will come back. So for people who use MATLAB or also any other programming language, don't confuse matrices in your programming environment with mathematical matrices. So we're talking about mathematical matrices here. And that's something different than, for example, a matrix in MATLAB. Or an array in Python. So mathematical matrices are different entities, and for example, they only exist there are only two-dimensional matrices. So mathematical matrices are two-dimensional, you can, of course, have three-dimensional arrays and so on, and you can use programming concepts to work with matrices or to emulate matrix computations, but they are not the same thing. Use them. How you calculate with matrices, maybe, or arrays, definitely arrays in your programming language are different from what I'm telling you about the mathematical things, but we are discussing the mathematical background here. There will be bits and pieces on Python code. Python is not, I don't think it's really nice for matrices, and might still need some time to be really good for matrices. Numpy, so I will show these things. I have seen that there was an introduction to Python. So in case you are okay with Python and you have Python open and available, you can also, once I show you these things, try to type them in and see where you're getting. Maybe we also take some time for that later, but let's see. Yeah, so if you have Python open on the side, feel free to go about typing there. Good, then let's go. What is a matrix? A matrix is a rectangular array of numbers, and it's denoted as shown here. Always I will use capital letters for matrices, and matrices comprise numbers, which are usually represented here by symbols. Here, this A symbols, these little A's here, and they have indices. And the most important thing about matrices is to remember that the elements have a row and a column index, and the row index is always the first one, and the column index is always the second one. Sorry. Here, for example, the element A12 is in the first row of this matrix A and in the second column. I hope there are not too many typos in terms of the N's and the M's, because I had to switch them from the multivariate course where I had these slides for. Anyway, so far it looks okay-ish, and the mathematician in the room will always point out, and everyone else also, if there's an index swap. So here, let's look at an example first. Here you have a matrix, so you have numbers organized here in this rectangular array, and this has 4 rows and 4 columns, and it says that the entry in the third row in the second column is 4. That's this 4 here. Matrices, of course, don't need to be square as shown here, so they can have more rows than columns, or more columns than rows. The number of rows and the number of columns is kind of what one refers to as the size of a matrix. And it's always important, important to remember that always, if you talk about indices, it's always the row index and then the column index. I assume that most of you have seen this. Who has seen this? Good. So we're starting not completely from nothing. I will talk about the size or the dimension of a matrix, and then usually, so I think throughout these 2 days, there will always, the number of rows will always be n, and the number of columns will be n. If they are the same, we call them square matrices. And in matrices, you can have different kinds of numbers. We are only interested in real entries, so our entries are the real numbers, although if you have them on a computer, they will usually be rational numbers. Yeah, we talk about real matrices. So that means matrices with real entries, so no complex numbers there. And I will denote the set of a real matrix or the set of matrices with n rows and m columns as r to the power of n times m. And this is a notation that I will use throughout. So R in the set means that R is a real matrix with 2 rows and 3 columns. So this is quite essential. Math is also, so math is simple. Math, if it's not simple and if it's not clear, then it's not math. So fortunately, there are no physicists here, and physicists don't really care. They write equations and so on, but never really specify what these things are. And in math, you take care to specify what things are. And so we will always specify, or most of the time, unless it's clear from the context, how our matrices are set up. And then, of course, you can have a matrix that only has 1 row and 1 column, but that's then just a single number, also called a scalar, and that's then just a real number. And that's already important, matrices with a single column, we also call n-dimensional vectors. Yeah? We are not going to discuss any vector algebra and vector intuitions, these things that you might know from school, like with arrows and how you add them and so on. So we don't do anything like that. Also find stuff on that online. Yeah, I will refer to a matrix with a single column also as a vector. Okay, I think that's fairly straightforward. That's what a matrix is. Any questions about what a matrix is? Okay, so one can calculate with matrices, and that's what I call matrix operations. I have a tendency to call it matrix calculus, but that's actually something different because that's about derivatives and so on. So one can compute with matrices. So one can do things, namely one can add and subtract matrices of equal size. That's what's referred to as matrix addition and matrix subtraction. Fairly straightforward. We will see that in a second. We can multiply a scalar, so a number in a matrix. That's called scalar multiplication. An important thing, although it's a little bit arbitrary in the beginning, is that one can swap matrix rows and columns. That's transposition. And so these 3 things they are straightforward, and you will have no problem getting into that. These other 2 things here, namely multiplying matrices with one matrix with an appropriate second matrix, matrix multiplication, and dividing by a matrix, that's a little bit more time consuming to get into it. Who's familiar with matrix multiplication? Okay. You all need to get familiar with matrix multiplication. I will tell you about what it is, but you will also need to practice that a little bit if you are using matrices to analyze data, which you are, I guess, doing. So, but let's first do the 3 things that are fairly straightforward, namely addition, scalar multiplication, and transposition. So the way I present these operations here, you may or may not appreciate. So if you don't know how to write functions, and if you don't like to see operations in terms of functions, then this first line here might not tell you much. I'll tell you in a second what that means. But these things here, then they are important. So the basic thing about matrix addition and subtraction is they work element-wise. Yeah. So that means 2 things. First of all, you can only add 2 matrices if they have the same size. You can also subtract only 2 matrices if they have the same size. And if you the matrix that you get from adding 2 matrices is a third matrix. So like if you add 2 and 3, you get a third number, namely 5. And this third matrix that you get is consists of the elements that you get if you add all the elements of your 2 matrices. And I will show examples, but here in kind of abstract form, So R and B are two matrices. They have the same size, n times m dimensional. And if you add them, so if you write A plus B, that means the matrix that you get consists of the elements that are the respective additions of these elements. So for example, let's check my indices here. Second row, mth column, and here also second row, mth column in the matrix that you get, you have the sum here. So that also means that it really means you can only add them if they have the same size. If they don't have the same size, you get an error if you try to do that in a program, and also you get an error in your head if you try to do it by hand. Matrix subtraction works the same way, also element-wise. So I don't say much about this. I promise you that I tell you what this here means. But that's how we write functions. So there you have a function symbol, and then you have the set, so the domain where the function takes elements from. In this case, it's the set, so the Cartesian product of all matrices, so of two matrices. So you have the n times n matrices, and you combine them with all the other n times n matrices, and you get an n times n matrix back. So you take two matrices in, and what you get out is a third matrix. But you can ignore that if you're not happy with that. So let's look at examples. So if we have 2 times 3 matrices, here we have 2 rows and 3 columns, and these are the numbers that we have. 2 minus 3, 0, 1, 6, 5, and 4, 1, 0, minus 4, 2, 0. Now, if we want to add them, we add their elements. Yeah? So 2 plus 4 is our first element here. Minus 3 plus 1 is our element here. 0 plus 0 is our element here. 1 minus 4 is minus 3, our element here. 6 plus 2 is 8 here, and 5 plus 0 is 5. Yeah, so that's not really tricky. Are there questions about adding two matrices? No. It can only work if they have the same size. You do it in an element-wise way. That's it. Subtraction, same thing. So I'm not going to do that now, but that's what you see here. Of course, if one gets into matrices, it makes sense to do these things by hand, but of course one also wants to check whether one does the arithmetics correctly. So it makes sense to be able to do that in some kind of programming environment. As I said, I think Python and Numpy, they are not awesome for matrices. They want you to do all matrix calculations on arrays. They also have a matrix multiplication operator now, which is good. It doesn't work all the time for everything that you want. They have a matrix class, so you can also define, instead of defining an array, you can define a matrix. But they say you shouldn't use it. So they say it's outdated and you shouldn't use it. Although it sometimes actually works better, especially for if you have matrices of a single column, than the array class. MATLAB, of course, is awesome for matrices because that's what it was built for. But of course, there's also some movement in neuroimaging to go to open languages, and also for people who want to have a career in data science and not only cognitive neuroimaging or engineering. Knowing about Python is definitely more helpful than knowing about MATLAB. So you define matrices in Numpy using this NP array, and then you type in basically the numbers that you want. And here we have two matrices then defined. You need these double brackets. I think you had I saw this course on Python. Who attended this Python course? No one. There was a course on Python, right? So somebody gave a Python course. If you never, who is working with Python? Okay, so at least some people know that. Of course, it looks similar in MATLAB, and it also looks similar in R. There are these little things. Yeah, I'm basically showing to you things here, and then you can, of course, work on them and get into that. So matrix addition in Python, you just do with plus. So after you defined two matrices, you just write A plus B, and then you get the element-wise addition, or A minus B, and you get the element-wise subtraction. So all fairly straightforward. Of course, in Python, for those people not familiar with that, you always need to import the package or the toolbox that you want to use. So if you want to use Numpy, you need to import Numpy first. Good, so that's addition and subtraction. Straightforward, element-wise things. Also very straightforward is scalar multiplication. So if you have an n times n matrix and a scalar, and as I already said, by scalar I mean a single number, you can multiply this number and the matrix. You can actually multiply it for the scalar with the matrix or the matrix with the scalar. It's the same thing, so it's actually commutative, which I didn't write down here. And it's also an element-wise operation. So if you have a matrix, let's look at an example here. If you have a matrix here with these entries and you have a scalar -3, then if you multiply this, then what that means is that you multiply every entry of this matrix with -3. So 3 times -3 is -9, 1 times -3 is -3, 1 times -3 is -3, and so on. So 3 times -3 again is -9, 4 times -3 is -12, and 2 times -3 is -6. Yeah, so also no magic there. That's scalar multiplication. Can be done in Python with the standard multiplication operator, which is the star. So there's really not much to talk about. Matrix transposition is something that is somewhat arbitrary, but exists for matrices and can be used and is often used. It means that you swap the rows and the columns of a matrix. So if you have, for example, this matrix here and you have the first row, if you transpose it, and I will always write this little t here, so this superscript t for the transpose of A, that means in this no, that's actually a little bit wrong here. So that doesn't quite make sense. So this is what the matrix is supposed to be, and this is its transpose. But yeah, sorry for that. That's not quite what I intended to say here. But if you look at what you see in the matrix, it makes sense. So you have the first row here, and if you transpose it, it's the first column. The second row here, if you transpose it, it's the second column. Let's look at a concrete example. Here you have the matrix R, 2, 3, 0, 1, 6, 5, which is a 2 times 3 matrix. Now, if you transpose it, the first row becomes the first column, which also means that your transpose has 3 rows, and your second row becomes the second column, and which means that you then have 2 columns. The things that are on the main diagonal here, so this 2 and 6, they actually are left unchanged. So one thing to note is that if you transpose an n times m matrix, what you get is an m times n matrix. So the size, so the number of rows and number of columns swap. If you transpose a 1 by 1 matrix, nothing changes because you have just a scalar, which is in the first row and the first column, nothing happens. If you transpose again, so if you transpose this matrix here again, that means your first, depending on how you want to see it, your first row becomes your first column, your second row becomes your second column, and your third row becomes your third column. So you're back to where you started. So the inverse operation of transposition is transposition. And that's what you need to know about matrix transposition. In Numpy, you do that with this kind of operator notation. You put a dot and a t behind your matrix, and then you get the transposed matrix. Good. So these were the 3 or 4 fairly straightforward operations. Are there any questions about addition, subtraction, scalar multiplication, transposition? We will use them all the time. Yeah? So they need to be clear. And of course, you can later on ask again, we will need them. Good. So the crucial thing, the first crucial thing about matrices is to multiply 2 matrices. And that's what is happening all the time in the GLM or everywhere. If you look at the implementation of things. And it takes a little bit of practice to be able to multiply 2 matrices, but once you can do it, then you will not forget it, and then you will of course always do it using some programming language. But it makes sense to first really sit down and multiply a couple of matrices and internalize this process. Okay, let's hope my indices are fine. The examples will be fine. So what does it mean to multiply 2 matrices? It's not an element-wise operation, yeah? So it's not that you multiply the entries at the same location and that's it. That also exists. This is actually called the Hadamard product of 2 matrices of the same size, but this is not what matrix multiplication is about. Matrix multiplication is essentially kind of encoding linear functions, if you want. It's very closely related to linear combinations, but we don't need to go into that. So we look at the operation. So the first thing to note is that you can only multiply 2 matrices if the first matrix, here R, has as many columns as the second matrix has rows. Yeah? So these inner dimensions, they always must be the same. And inner dimension, I mean here this M and this M. Yeah? So we take an N times M matrix and we multiply it with an M times P matrix. The N can be whatever we want, the P can be whatever we want, but these inner dimensions need to be the same. Otherwise, matrix multiplication is not defined. And if you do it in programming, you will get an error, and that's an error that you get a lot. Or at least I get a lot if I try to multiply things. And then Python says this, although it's one-dimensional, anyway, Python is so that's the first thing. What you get out, and that's also something that you should then also remember right now, is you get a matrix of the size of these outer dimensions. So if you multiply an N times N times M matrix with an M times P matrix, you get an N times P matrix. That's always the case. Yeah. So, for example, if you have N times 3 matrix, and here you have a 3 times 1 matrix, you get an N times 1 matrix out of that. Let's make it more concrete. You have a 4 times 2 matrix, you have a 2 times 1 matrix, you get a 4 times 1 matrix, so a vector out. That's always the case. So what are the entries? The entries you get from an operation that you need to get your head around. You take, we start here with the first element. What you do is you take, for this element, you take the first row, you transpose this row, so you swap it by 90 degrees and overlay it on the first column of the second matrix, yeah, in your head. And then you do an element-wise multiplication of the things that are on top of each other. So A11 times B11, A12 times B21, and so on until A1M times BM1. And this is also why you need the same number of columns as you have rows here, because you need to find the matching elements. And if you have more columns here than you have rows here, then at one point you run out of elements in B. You multiply those, so this is what's shown here, A1I, BI1, you multiply them, and then you add them all up. Now, if you remember what a scalar product is when computing with vectors, this is forming the scalar product, Scalar Product, or dot product, I should say dot product, the dot product of this vector here, if you actually transpose it, because it needs to be a column vector, with this column vector. Yeah, so, and that's this entry. The next entry you get from staying with this row and going to the second column here. So again, you take this row, swap it in your head by 90 degrees, overlay it here, multiply all the elements and sum them up. And you do this with the first row of A until you are at the last column of B. So at one point you will do this and this. Which also means, as you're staying with this row, you do that until you're at the end of the last column of B. That also means that, as I already said, you end up with as many columns as B has columns, so this P here. And then you have computed the entries in the first row. Then you go to the second row of A and do the same thing all over again with the second row of A. And there you get the elements of the second row of your output matrix. And then you do it for the third, and so on. And in the end, you will do it with the nth row of A, with all columns of B. And hence, your last entry here will be the nth row. And hence, you have as many in your output, as many rows as you had in A. That's how that is defined. In general, that's also something you should note here. It's not commutative. That means A times B is not the same as B times A. Most of the time, B times A might not even be defined. So if we have P equals 2 and N equals 3, then that would mean we want to multiply an N, M times 3 with a 2 times, so the M will be the same. Let's do an example. 4 times 2, 2 times 3. If we would do it the other way around, we have 2 times 3 times 4 times 2. And then the inner dimension just wouldn't match. So it's not commutative, and that's very different from multiplication as you know it, right? So if you do 6 times 2, that's the same as 2 times 6. But for matrices, that's generally not the case. There's another type. What's written here is what I explained. So let's do that. Add an example. So these are two matrices. And we first see that there are 2 rows and 3 columns in this matrix. And here there are 3 rows and 2 columns. So we can actually, so we have a 2 times 3 times 3 times 2. So we can compute A times B. We can actually also do B times A, because this 2 and this 2 also match. And what we get are 2 times 2 matrices or 3 times 3 matrices based on this Eselsbrücke. There's no reason Eselsbrücke, but it's helpful. Good, so let's have a look. A times B. So 2 minus 3 is 0. We want to compute this first element here in the upper left corner. So we do 2 minus 3 is 0 and consider this column here. And as I said, we swap this in our head by 90 degrees and overlay it here. So we have 2 times 4, minus 3 times minus 1, and 0 times 1. And then we add them all up. So that's 8 plus 3 plus 0. Then we are at 11. And then we go to the next entry here. So 2 minus 3, 0 times this column. So that's 2 times 2, minus 3 times 0, 0 times 3. And that's 2, 0, 0, 4. So 2 times 2, 4, 0, 0. So we get 4. So we've done everything that we need to do with the first row of A, and then we go to the second row of A and do the same thing again. 1, 6, 5. 1 times 4, 6 times minus 1, 5 times 1. And that's 4 minus 6 plus 5. And that's 3. And then we do the last thing, 1, 6, 5 with 2, 0. 1, 2, 3, 6, 5, 3, 0, 15, 17. Yo, that's how that works. In Python, you can do that with this add operator. So the add symbol that you know from email. Of course, also in any programming language where you multiply matrices, the dimensions need to match. So if you have, so the inner dimensions need to match. If that's not the case, you get an error. So here I'm trying to multiply a 3 times 2 with a 3 times 2 matrix, and here the inner dimensions are different, so that doesn't work, and I get an error, as I should. So here's another example, which I'm, so the other way around, which I'm not doing right now. Yeah, so that's matrix multiplications, and that's really important. Do you have questions about this? Okay, so really try to, so the first thing is that, or the first thing that you always need to figure out is what's the size of the resulting matrix, because that's, before you start doing anything by hand, figure out what's the size that you get, because then you see much clearer what the things that you see as abstract symbols on in a math text actually mean. So that's important. And then, yeah, do it a couple of times, multiply matrices, then you will forget it again, do it again, and so on, and then check your calculations using Python. Good. So the people online, if you have questions, just write something into the chat, right? Okay. Now, there are, so we have basically, except for inversion, we have everything that we need. There are some rules of matrix algebra that we will also use in things that I will show you. Addition and subtractions are associative, so it doesn't matter because this also, of course, because these are element-wise operations. So plus minus, I mean, it doesn't matter whether it's plus minus. It doesn't matter whether you first add A and B and then add to that a matrix C, or you first add B and C and then add a matrix A, because that's of course happening all at the level of the elements. And there you know that 2 plus 3 is 5, plus 7 is 12, but you can also do 7 plus 3 first, plus 2, and then you get 12. Addition and subtraction are commutative, as are these elements entries. If, and here I assume all the time, of course, that it's appropriate, so that you can multiply A times B and A times C. If that is the case, so if the size is appropriate, then also this distributivity holds. So A times B plus C is AB plus AC. That's also following from the elements. And one thing that is a little bit more advanced, or yeah, maybe more advanced to actually show, but can also be shown, of course, as all things. So I don't prove them here because that's what you can do in linear algebra. I'm just stating them. One thing that we will also see a couple of times is that if you multiply two matrices, A times B, and you consider the transpose of this product, that's the same as the product of the transpose of B and the transpose of A. And the order here switches. So A, B becomes B, A, and both of them are transposed. Yeah? So that's a little bit more there. You would have to actually write down a little bit more to actually show that. So I'm not showing that now, but we will need it, and it's also quite okay to remember because it has this kind of form. So you have AB transpose is BT AT. Good. So that's then already quite good. What time is it? The time here, because we have to discuss one more operation, and that's all fine. We're actually doing quite well for time. the last thing that we need to discuss is matrix inversion. So we now know how to add and subtract matrices, how to do scalar multiplication, and how to multiply two matrices if that's defined. And there is something like dividing by a matrix, but that's not really called matrix division, but it's called matrix inversion. And that's also crucial. It's kind of motivated, and like everything in matrices is motivated from systems of linear equations. So things that you did in school, that's where all this is coming from. And this is here my little intro to matrix inversion. You will not be required to here or anywhere to do matrix inversion by hand. That's what you do in a linear algebra course. Usually in applications, you use algorithms that are implemented in your matrix calculation environment to invert matrices. So what is matrix inversion about? And that's what we are going to discuss now. So we start with this example here. We have an n times n matrix A and an n times 1 vector or matrix X and an n times 1 vector B. And we assume, for the sake of the argument that A and B are known, but X is unknown. And here's our example. A is 1, 2, 3, 4, and B is 5, 11. And now we consider this system of equations here, AX equals B, where we know A and we know B, and we don't know X. And of course, we want to find X, like in math, one wants to find something. If we write that out, we have kind of this matrix here, 1, 2, 3, 4, times the entries of X, X1, X2 equal 5, 11. Of course, we can also write this out further, because this is, of course, here using a matrix product. So we can just write out the corresponding equations. So 1 times X1 plus 2 times X2 here equals 5. That's what this says here, and 3 times x1 plus 4 times x2 equals 11. So that's the system of linear equations. So two equations with two unknowns, and that's the matrix encoding of that system of linear equations. So we have a system of linear equations with two equations and two unknowns. And some typos. And we want to figure out for which axis this holds. And these are things that you did in school. So there are different ways to do that, and it's not always possible. And there's a whole theory about solving systems of linear equations. We want to take from that a little bit more an intuition for our inverse. So for introducing inverses, we now make a further assumption, namely that our matrix A is scalar, so it's a single number. X is also scalar, and B is also scalar. And we are considering just this equation here: A times X equals B. So, for example, here's an example: 2 times X equals 6. Yeah? So, what would you do to solve that? To figure out what X is? Well, you would divide by A on both sides. Then, if you divide by A here, the A goes away, and you only have the X, and here you would have B divided by A. And dividing by A, as you remember from school, is the same as multiplying with the multiplicative inverse, or the reciprocal of A. So multiplying with 1 over A. And how is this 1 over A defined? Well, it's the thing that if you multiply it with A, gives you the neutral element with respect to multiplication, which means 1. If you multiply any number with 1, you always get the same number again. So that's what's called a neutral element. So here we would have A equals B, and then we would multiply with the inverse of A, so 1 over A. And then here we would get 1, A to the power of minus 1, which is 1 over A, equals 1. And on the other side of the equation, we have 1 over A times B. So here it's spelled out again, 1 times X, and here we have A minus 1 times B, which is X equals BA. So here, for the concrete example, if you have 2x equals 6, we multiply with the multiplicative inverse of 2. So 2 to the power of minus 1 times 2 times x. And here we do the same thing on the other side of the equation. I guess you remember that you always have to do the same things on both sides of the equation to make sure that the equation still holds. So we have 2 to the power of minus 1 times 6, which is the same as, or equivalent to 1/2 times 2x and 1/2 6. So you divide both sides by 2. Then here you get 1. So there's only the x, and here you get 3. Yeah. Of course, you see already here that the x that you're looking for is 3, but that's what you formally do. Now, why am I telling you this? Because the matrix inverse is defined in analogy to this multiplicative inverse, or the reciprocal of this number here. Namely, it's defined as a matrix. First of all, it's only defined for square matrices. So it's defined as a square matrix that if you multiply it with the original matrix, you get 1 out of it. You don't really get 1 out of it, but you get a matrix that doesn't do anything if you multiply it by it. So you get a neutral element with respect to matrix multiplication out. And now if you're going back to this thing here, if you, in principle, although you don't know how to compute that or anything, but if you somehow know that a to the power of minus 1, so the inverse of a times a gives you 1, whatever that means, then you would only have x here, and on the other side you would have this multiplication with the inverse of a. So that's the kind of motivation for, well, that's kind of an intuitive approach to matrix inversion. I will give a definition in a second of the inverse of a matrix. Do you have questions about this example? Is this everything clear, or you're already zoned out, or this example was fairly clear? No? Okay, some people nodded. Okay, then assume that some people for that it was okay. So again, the basic motivation is here. You have 2x equals 6. You want to find x. Okay, you need to divide by 2, which means you multiply by the inverse of 2, which is 1/2. And then you do that on both sides, and then you get only the x here, and you divide 6 by 2, then you get the x. Now, you don't really get 1 if you multiply an inverse of a matrix with a matrix, but you get what is called the identity matrix. The identity matrix is a fairly simple matrix. It's a square matrix. So we're talking about n by n matrices here. And the identity matrix is the matrix that is everywhere 0 except on the main diagonal. So it has entries on the main diagonal, and they're all 1. Now, with the special thing about this identity matrix is that if you use it in matrix multiplication, so if we use the identity matrix, which I denote by this IN, with any matrix, either from the left side or from the right side, not any matrix, sorry, n times n matrices. We're talking about square matrices only at this point. I will also make this fairly explicit on the next slide. Then we get the same matrix out. Yeah. So if we, for example, have a 2 by 2 matrix, and we use the 2 by 2 identity matrix here, 1, 0, 0, 1, and we multiply this 2 by 2 matrix by this identity, we end up with the same matrix as we did before. So yeah, maybe I show that briefly, because here I only have the if we have chalk. No. Yeah, I only have the more formal proof, but so yeah, it doesn't really help if I try to tell you to imagine that, but do it. Take a piece of paper and write as one matrix 1, 2, 3, 4, and next to it 1, 0, 0, 1, and multiply them. Do it now. It's the interactive part. Yes, again, the example.
I think also if you press that saving, you can use a board in Zoom, and you can
Not sure.
Maybe it's one idea.
Has anyone tried it? Okay. Apparently you don't want to do practical stuff. Here's the proof. So essentially, and there's a little bit of a typo also. Yeah, it's just, if you think what you're doing, so if you have here the first row and you multiply with the first column, of course, everything in your sum will be 0 except for one entry, and that's exactly the entry that you already had. If you're doing it with the second row and any column, you only are left with the entry that you have there in the second row. So yeah, it works. Now, the crucial thing why we need the identity matrix, and we will also sometimes see it, is that it features in the definition of the inverse of a matrix. And there are two things of note here. First of all, when we're talking about matrix inversion, we only talk about square matrices. Yeah. So we are not talking about n times m matrices it's here, but n times n matrices. And a square matrix does not need to be invertible. So like sometimes there are no solutions for systems of linear equations, but it can be invertible. And if it's invertible, or it is called invertible if there exists a matrix a to the power of -1, which is also square, such that if you multiply it with a, gives you the identity matrix, whether you multiply from the left or from the right. And this a to the power of -1 is called the inverse of a, or the inverse. If you have a scalar, that is then just 1 over a. The somewhat maybe confusing thing, or maybe not that nice thing about this definition, is that it just tells you what the inverse of a matrix does and how it's defined, but it doesn't tell you how to compute it. Yeah? So if I give you a matrix now, you don't really know whether it's invertible at all, and you also don't know how to compute the inverse. How to compute the inverse? There are different algorithms for that, yeah, you can to do it by hand. We also have something online that you can look at. In the end, you will not do it by hand anyway, so you can use commands to do that. Here's a little bit of an example that at least shows you that if a matrix inverse exists, how yeah, it behaves. So if we have this matrix here, 2, 1, 3, 4, then the inverse of this matrix is, or I'm telling you that the inverse of this matrix is 0.8 minus 0.2 minus 0.604. Why? Because if we multiply these, we get 2 times 0.8, that's 1.6, minus 0.6, that's 1. If we do 2 times minus 0.2, we get minus 0.4. If we get 1 times 0.4, we get 0. And here, if we add that, we get the 0. Here we get 3 times 0.8, 0.24, and we subtract from it 4 times 0.6, so 0.24 again, so we get to a 0, and here we get to minus 3 times 0.2, so minus 0.6, and plus 1.6, so we get to 1. So that's how you can check that this is the inverse of this, because if you multiply them, you get the identity matrix. Sometimes it doesn't work. So for example, this matrix here, although it's square, it's not invertible, which is also called singular. Because if it would be invertible, then there would be a matrix A, B, C, D, such that if you multiply them, and that would be 1, 0, so you get A, 1, 0, so you get B, and you get only zeros here, that this thing would be equal to the identity matrix, but clearly there's a 0 here and there's a 1 here, so that doesn't work, so that's a contradiction, and this matrix is not invertible. Yeah. So again, both of these examples, they don't show you how to compute the inverse of a matrix. They just try to explain a little bit more what the matrix inverse is and what it does, and that it can exist or cannot exist. There are algorithms to do that for 2 by 2 up to 5 by 5 matrices, and you can ask the mathematician or anyone who took a linear algebra course to how to do that. You can also do it. It's semi-fun, but then you did it. But of course, in general, if you work with matrices, you invert using matrix inversion schemes, which then implement the algorithms that you also use by hand, but usually in a fancier and more robust way. In Numpy, you can invert with this linalg module of Numpy, and specifically this function inf. MATLAB, same thing. In R, I think it's also inf, or you need to load something. So here's the example that I showed you. So here we define the matrix, and then we invert it, and we get what I just showed you. And this other matrix that is not invertible, if you try to invert that, that's really not invertible. So you have a singular matrix. Good. So that's matrix inversion. Are there questions about matrix inversion right now? Okay, then I suggest we take a break, or do you want to continue? So where are you right now in your head? So I could go on for half an hour and then we take a longer break, or we take a break now and then go fresh into determinants and special matrices. Who wants a break now? No one. Good, then I continue with determinants. So, but let's first summarize again what we did. So we have all the matrix operations that we need, we have to our disposal now. So we can add matrices which have any size but the same size, and we can subtract them. We can scalar multiply them. We can matrix multiply two matrices if the first matrix has the same number of columns as the second matrix has rows. And we can invert square matrices, only square matrices. The inverse of a matrix, of a square matrix, is that square matrix that, if multiplied with our original matrix, gives us the identity matrix. Yeah, so that's what we have learned thus far. Now we, review a little bit. So there's of course much more in linear algebra and on matrices that one could discuss. I want you, because I want to show you the multivariate Gaussian in the second part. I want to briefly remind you what a determinant is. It's not really crucial and we will not use it much, but there will be a determinant in our multivariate Gaussian, so why not have a look at it? So that's the general definition of a determinant, but I think we can actually skip that and focus on the determinants of 2 by 2 and 3 by 3 matrices. So determinants are defined for square matrices, and they can be used as a check to figure out whether a matrix is invertible or not. If it's 0, the determinant, then the matrix is not invertible. If it's not 0, then it's invertible. Determinants can do many things. You can also use them to solve systems of linear equations. You can also interpret them as giving you a volume of the column space of a matrix, but I don't introduce these terms, so we can't really do anything with that. If you might remember from school, we have an example here. You might remember from school that you compute the determinant of a 2 by 2 matrix by multiplying the diagonals and subtract, so the normal diagonal, so 2 times 4, and subtract from it 1 times 3. So you kind of multiply this way and you multiply this way, and this is positive and this is negative. So here the determinant of A would be 2 times 4 minus 1 times 3. That's 8 minus 3, it's 5. That's also an important thing about a determinant. It's a number. We get a number out of computing a determinant. And here it's 5. We've already seen that we can compute the inverse of this. Here the determinant is 1 times 0, that's 0 minus 0. It's 0 again, and the determinant is 0, and that implies that the matrix is not invertible. Why? It's of course something that you need to prove. That's not trivial to see or something, but that's something we are of course not doing here. Now, if you might have also in school seen how you compute determinants of 3 by 3 matrices, there it gets a little bit more advanced. So you take the first leading diagonal, multiply them, you add to that the diagonal that you get from putting the first 2 columns here next to the matrix, and then continuing your diagonal up to here. So A12 times A23 times A31. And then you do that once more with A13, A21, and A32. And these you all count positive for your determinant. And then you subtract from them what you get on the counter diagonals if you want. So A12, A21, A33, A11, A23, A32, and A13, A22, A31. So that of course gets quite easy if you have a matrix like this. So if you imagine these first 2 columns next to this, whether you imagined or not, you will get zeros anyway. So here you have the 2 times 1 times 3, that's the first diagonal, and then you have 0 times 0 times 0, and then you have 0 times 0 times 0. So you only get what you have here in the first place. And if you have these things next to it, there will also be zeros in your product, so everything gets to 0. So the determinant of a diagonal matrix, which I haven't really formally introduced, but a diagonal matrix is a matrix that is 0 everywhere, but has non-zero entries on the diagonal. That's always just the product of the diagonal. And that's actually something that we will need later on if it comes to multivariate Gaussians and independent univariate Gaussians. So maybe remember that the determinant of a diagonal matrix is just the product of the diagonals, diagonal entries.
Can I ask also something here?
Sure.
For the GLM design later in ILM, we need to use like many of these operations? Or?
Yes.
Okay, so
it's very important. Yeah. I'm not doing this for the fun and because I think math is great. Of course, math is okay, but I'm doing that so that you know what the GLM is about.
Okay,
right.
Just
to
know what's coming.
Yeah, and you can compute determinants also with Numpy. Of course, there's the det function. Okay, so that's basically everything I wanted to say about determinants. There's much more one could discuss. Who has seen this for 2 by 2 matrices in school? Remember that? No, you never heard in school about determinants? Really? Doch. Das haben wir so, also ich will jetzt nicht sagen, dass früher in den 90ern war alles besser, aber also wenigstens so 2x2 Determinanten haben wir gemacht in der Schule. Anyway, so determinants, it's somewhat tricky in linear algebra how to deal with determinants, because you can also do linear algebra fine without determinants actually. We will, however, see a determinant, so that's why I included it. A little bit more important for the rest, no, but equally important, I think, are these special matrices. And this is mainly notation. So first of all, we will see zero matrices. These are matrices that only have zeros as entries. And I will denote them as 0 and n if it's an n times n matrix. So for example, 0, 3, 2 means 3 rows, 2 columns of all zeros. 0, n means a single column of as many zeros as it says. So 0, 4 would be 0, 0, 0, 0. Fairly straightforward, but we will see 0 n quite a lot. So always think of a vector here with all zeros. And the same thing for ones. And we will also there see, for example, something like 1, 5 means 5 ones in a column, or a 2, 3, there's an equal sign or definition sign missing, means all ones in a 2x3 matrix. So that's essentially just notation, but we will see it quite often. And then there are two matrices types that are interesting and that we, or three that we need, at least know the name, namely symmetric matrices. A symmetric matrix is a square matrix that if you transpose it, doesn't change. Which means that kind of the elements that have interchangeable row and column indices are the same. So for example, here in the second row and the third column, so the element 2, 3 is the same as the element here 3, 2, namely 5. So if you think about transposing this, you take the first row and you get the first column 2, 1, 3. 1, 4, 5, you transpose, you get the first column, 1, 4, 5, 3, 5, 6, you transpose, you get 3, 5, 6. So it's a special type of matrix. Of course, not all square matrices are symmetric. This is an example of so most of the matrices are not symmetric. So that's 2, 3, 1, 4. If you transpose it, you get 2, 3, 1, 4, which is different from 2, 3, 1, 4. So these two matrices look different. So that's symmetric matrices. Diagonal matrix, we already introduced informally. So these are matrices that only have zeros, but on the main diagonal, where you can have any kind of entries. So for example, this is not diagonal because there's no zero here. Why are they interesting? Well, symmetric matrices we will see as covariance matrix parameters, diagonal matrices also as covariance matrix parameters. And of course, dealing with them is simple. For example, the determinant, as we already the determinant of a diagonal matrix is just the product of the diagonal entries. So symmetric and diagonal matrices we will need. And then one thing that we will also need, but where the theory is actually much deeper than we're going into here, is the notion of positive definite matrices. Because in Gaussians, the covariance matrices are always positive or need to be positive definite matrices. So they cannot be not positive definite matrices. What are those matrices? They are square matrices that are symmetric, and for which holds that for all n-dimensional vectors, this thing here, which is the product of X transpose with the matrix times X, is larger than 0. What's the size of this expression here? So in terms of the matrix size. If X is n times 1 dimensional, C or has the size n times 1, and C has n times n. And you multiply xt times C times X. What's the size of the resulting matrix? Do that on paper with the rule that I gave you. Now. Put the cookie down. Nobody knows that. Do it with, so let's switch back. You have this rule here, or that's the rule that I'm referring to. And of course you have two products here, first xt times c, and then the result of xt times c times x. That's the rule. And again, x was n times 1, and c was n times n. Has anyone done it? You can also do it by an example. Take x to be something simple. Use zeros, and it's easy.
But this is 3 matrices.
Yeah, it's so 3, but you first do xt times c, and then you get...
What's the rule for multiplying 3 matrices?
No, the rule is for 2, but you can, of course, use the rule twice.
But what do you do first?
In this case, if you look into, so it doesn't matter. But you see that this is 1 times n, and this is n times n, so you can do this, or you can do this n times n times n times 1. It doesn't really matter. Some people suggest that it's 1 times 1. I love interactive parts. Anyone succeeded? No? So what you, of course, have here, have somebody who doesn't know how to work with Mac, and you have this thing here, this xt, that's the transpose of an n times 1 vector, so that's 1 times n. And this is n times n. Now, if you do xt times c, you get 1 times n times n times n. So you get the inner dimensions match. So you get 1 times n, because the outer one is n. And then you have here xt times c is a 1 times n matrix, and you multiply it with an n times 1 matrix, namely x. So the inner dimensions are n, they disappear, and you get to a 1 times 1 matrix. And this is also why we don't have to discuss what this larger than actually means, because if that would be a matrix larger than a 1 times 1 matrix, we would have to define what it actually means for 2 by 2 matrix, for example, to be larger than 0. Could be that it's every element, could be that it's the sum of the elements, I don't know. So this is a 1 by 1 matrix for scalar, which is also something that features quite heavily in the Gaussian. So it doesn't hurt to appreciate that if you have an n-dimensional vector and you have a n times n matrix, and you multiply the transpose of this vector with the matrix, and then again with the vector, you get to a single number. Yeah, and if that holds for all x's, then this is called positive definite. This, of course, means that in principle, if to check whether it's a symmetric matrix, you need to check all the x's. And of course, there are infinitely many. So there are certain tricks to check whether something is positive definite. Yeah, we will not go into that deeper, but I can also not say that the covariance matrix parameters need to be positive definite, because the covariance matrix parameters that we will see in the second hour, on the second part, are always symmetric, and they need to be positive definite, like the variance parameter of a Gaussian needs to be positive and not 0. Yeah, and then also these positive definite matrices have some nice properties, many nice properties. So if you go to Wikipedia, you can look at all the nice properties of positive definite matrices. They are always invertible, so we will see the inverses of covariance matrix parameters all the time. Determinant is larger than 0, and one can actually take the square root, if you want, of these matrices. Namely, it's guaranteed that there exists a matrix K such that C can be written as K times K transpose. And this thing we will need definitely tomorrow. Good. So our special matrices are our matrices of 1s and 0s, symmetric diagonal matrices, and positive definite matrices. Of course, there are many more matrices, but types of matrices, but we keep it at that. Good. So that was the matrix part. The thing, of course, with foundations is that if you, like you asked, if you hear the foundations, you are like, yeah, that's nice, but why do I need it? And then you, one, and also myself, has a tendency to ignore it because it's not clear immediately where you need it. But then, and I can just tell you that, then once you get to something that you are interested in, or might be interested in, like the GLM for fMRI, the problem in understanding will come from the fact that you didn't quite, or I didn't quite appreciate or didn't quite get the foundations. So of course it's an iterative process. So you hear some foundations, don't know why, and then you hear something that you're interested in and you don't understand it, but you remember there was something in the foundation. So you need to get back to foundations. And that's a process that you can do for the rest of your life if you want to do academia. And it's a nice process. Good. Are there any questions about matrices at this point? We will see them all the time, and I guess questions will come up once we see them in action. Good. Then it's 11 now. So the next thing on Gaussians, that will not be too long. How long a break do you want? Quarter to 12. At 12 continue, so you can choose, let's vote. I could continue at 11:30, but I can also latest continue at 12. Who wants to continue at 11:30? Who wants to continue at 12? No one?
Let's go in between. Let's
Yeah.
go something in between.
Who wants to continue at quarter to 12?
Maybe if we know when we are having lunch and how long the...
But when is lunch? Is there lunch?
Mhm.
Yeah.
When is it?
Oh, we don't have it.
Yeah, I think it's when we want it, so we can have it now.
Well, it's a bit early.
But we can also have lunch then. Okay, yeah, who knows when lunch is? Is there lunch?
I guess after 12, but I don't
Yeah, maybe Esther is here.
Yeah. Because then we can now maybe, yeah.
It's not ready, but I guess after 12 it will be maybe.
Okay.
And we probably know.
Yeah, but maybe Esra, are you online? Can you tell us when lunch is? 11? Oh, well, that's what people say. When are we having lunch? At 11. Okay, then I say we start again at 11:30 and do Gaussians and maybe then 1 hour and then definitely lunch. Okay, so we continue at 11:30.